if you're on the live stream, it's going to look like I'm talking, but I'm not really going to be talking to you because I have to mute myself so I can make an announcement and gather. So you're not going crazy. I'm now back on the Zoom with my, the live stream with my voice, and we're slowly ramping up the number of viewers of the live stream. So we'll get started in just a few minutes with our next session. I see 3 different videos of myself in different delays. So it's very strange for me. So if I look this way, then I see the live stream. And if I look over here, then I see the Zoom and my thing, and each one is slightly off. And if I look over here in the corner, then I can see the gather video. So it's a very disorienting experience for me. Yes, I'm multidimensional, Jeff. With the YouTube live streaming analytics, I can see when people like as they do it. There's this little thing that pops up and says you gotta like. I can see how many concurrent viewers there are. It's very exciting. It makes me want to start live streaming my all my video game playing and whatnot and become a YouTuber. This this Racket game is why do this? Someone asks whether it is better for them to watch through Gather or YouTube Live. I think it's the same because the thing that on Gather is the YouTube live stream. Maybe if you're in Gather, you don't see the chat. I don't actually know. Yeah. Oh yeah, that's an interesting idea. I should live stream all my Racket programming. All right, I'm going to unmute the speakers for today for this session to give them a little introduction. So for this session, we're going to have 2 speakers. So first, there's Darragh. Say hi, Pierce.
Hi.
And next will be Gustavo Massaccesi.
Hi.
And like before, we'll watch their pre-recorded talks and type in your questions into the global chat or the YouTube chat or into the document. I monitor them all and I try to coalesce everything into the document. And then we'll do live questions for the live stream right after. And Pierce is the first talk, so he'll be in the Northwest region, discussion area A. And Gustavo is the second talk, so he'll be in the Northeast region, discussion area B. That's all the announcement for now. So I'm going to fiddle with everything again, and then we'll get the next set of talks going. Thank you very much.
Hello, my name is Pierce Darragh, and on behalf of William Hatch and Eric Eide, I'm very excited to present to you about our paper on Clotho, a new Racket library that enables developers to use parametric randomness with ease. So I guess the first thing we should address is, what is parametric randomness, and why should you care about it? Let's find out. In the paper, we define parametric randomness as a kind of random value generation that is amenable to predictable external manipulation. Practically, what we mean by this is any system of random generation wherein the user can deliberately influence the outcomes of otherwise random generation events to bring about discrete structural changes in the resulting output. In some sense, this is like being in control of the destiny of your program even when randomness is concerned, hence the name. Clotho was a Greek goddess responsible for spinning the thread of humans' lives that determined their fate. I think that definition of parametric randomness is not very helpful, though. I prefer learning by example myself. Here, we have a small Minesweeper game. If you don't know Minesweeper, that's okay. All you need to know is that it's a single-player game where the player attempts to identify the locations of a number of mines hidden across the board. For this implementation, the player is controlled at random, simply choosing any of the 9 squares until either the game is won, all squares without mines have been chosen, or an invalid move is made, such as choosing a square where a mine is hidden, or choosing a square that was chosen before. There are 3 mines hidden somewhere in these 9 squares. The player's objective is to select the other 6 squares without disturbing the mines. The first move the player randomly makes is A2, the top middle square. There isn't a mine, so it's considered successful. Nice! Let's make another selection. The player randomly selects B3, and it's also a successful move. And now B1, which is another success. We're really on a roll. Uh-oh. Looks like the player randomly selected B2, which was hiding a mine. Darn! And it was going so well, too. Well, it's about time we learn about this parametric randomness business. Let's replay the game, but while looking at the game's decision tree at the same time. Here, we're looking at 2 things. On the left is the current state of the game, and then on the right we see all of the available options that the player could make right now. The 3 squares where mines are hidden are shown with red backgrounds and a bomb. We hope the player doesn't pick any of these. The valid options that will progress the game towards a win state are shown with blue backgrounds and a gray check. We're just replaying the earlier game, so we'll move forward to when the player has selected the first square, A2. The player made the choice, which we see reflected in the current game state on the left. On the right, the options that the player didn't pick last time are shown slightly translucent in the top row of boxes, and the bottom row shows the available moves the player could make next. Note that A2 is an option for the player since we are assuming a naive implementation of the game, but taking this path would bring about an end to the game because it's an illegal move. However, we know the player randomly selects B3. I've eliminated the extra boxes from the first selection to reduce the visual clutter for the moment. But remember that we're only looking at one branch point at each level of the game. In actuality, all of the blue checkboxes have their own subtrees with many more potential paths through the game's possible states. It's quite complex. Anyway, we move forward to the player's selection of B1. Nothing surprising here, I think. But finally we come to the end of the game, when the player selected the square B2. A square with a mine hidden in it. Remember, there were a lot of other paths through this tree of possibilities. This could have played out very differently. If we wanted to, we could rerun the game from the beginning and hope that new random options would be chosen to select a different path through the tree. This is a common strategy when exploring a very large state space. You just make random choices and hope to stumble upon a branch that is interesting, which, in this case, would be a branch that ends in a win. We think this is a bad solution for some kinds of problems. For example, if we want our Minesweeper player to win, why should we throw away 3 perfectly good moves? Why start the exploration over at the root of the decision tree? This is inefficient. Clotho instead allows you to rerun the sequence of random generations, but mutate only specific outcomes so that you can explore more paths similar to one you've already explored. We are effectively reducing the size of the problem space by constraining our decision tree to a subtree with a predetermined prefix path that is known to be good. This reduces the number of possible explorations by a significant amount. To enable this style of random generation, Clotho associates each random generation event with a parameter, shown here in boxes labeled P with subscripts. These parameters are combined into some kind of internal representation, which can be used as an input to the game function or a driver function when that's easier. In this case, the particular combination of parameters resulted in the player selecting a square with a mine in it and losing the game. By modifying a specific parameter, the course of the program can be altered at a specific point. Here, we modify the parameter corresponding to the random selection that caused the player to lose the game. Now, the player selects a different square as the 4th move, but we didn't have to re-explore the whole decision tree to make the first 3 moves. Instead, we preserved those moves and simply made a new selection for the 4th move. Maybe this modification to the parameter will even cause the player to win the game. Now we can summarize what parametric randomness really is. In a parametrically random system, you can start by generating an initial sequence of random values, which are automatically correlated to parameters that are exposed to you. If you happen to like part of the result of that sequence of generations, but not all of it, you can tune specific parameters and rerun the program to observe the outcome. Doing this allows you to quickly explore decision trees for random problems where interesting paths are clustered together. We think this parametric random generation could be very useful in some problem domains, like our own, which I'll come to in time. So now that you know what parametric randomness is, let's talk about Racket's built-in support for random generation and see how we can make parametric randomness work. Practically all randomness in the Racket standard library is controlled through a single arbiter of random state, the current pseudorandom generator parameter. Influencing Racket's randomness anywhere requires manipulating this parameter. Note that this use of the word parameter refers specifically to the Racket concept of a value that can be modified thread locally without affecting external scope. There's a link at the bottom of this slide to read more about it if you're not familiar with the concept, but all you really need to know is that parameters are one way of providing singleton objects used for managing the state of something. Racket provides 2 ways to construct a new pseudorandom generator that can be used as the current pseudorandom generator. One creates a new random state with no user input at all, which is clearly not going to help us because we can't manipulate the construction. The other takes in a vector and uses that to initialize the state of the generator. Unfortunately, the rules for that vector shape are very specific, which means that we're really only setting the initial state and then letting the random generation follow whatever mathematical model it uses internally. We have no control over specific generation events. There is also the random seed function, which lets us manually set the seed from which random values are mathematically derived. Like the vector we just talked about, this function doesn't really give us fine-grained control over each discrete generation event, and that's crucial to achieving a simple parametric randomness system. These are essentially all the ways Racket provides to manipulate the random generation of values. So what can we do with this? Well, when we were initially trying to solve this problem, we saw 2 potential solutions. The first idea was to simply extend the pseudorandom generator in some way to support our desired functionality. If we could just build a new variant of the pseudorandom generator and install it into the current pseudorandom generator parameter, we should be able to use all the other existing randomness functionality in the standard library, as well as anything else, in addition to whatever extra functionality we wanted to provide ourselves. The other option was to build an entirely new randomness system from the ground up. Building a new system seemed like way more work for not much benefit, so we decided to extend the pseudorandom generator. Keep things simple. Unfortunately, we discovered that the pseudorandom generator is internally built as a struct that does not expose its fields or methods beyond its declaring module, and the current pseudorandom generator parameter will not accept a value that isn't an instance of this struct. But building an entirely new randomness system wasn't the right approach either. We wanted to be able to use parametric randomness with other libraries that relied on Racket's built-in randomness functionalities. If we built a new custom system, we would have to essentially re-implement those libraries to use it. Neither system was going to work for us, so we settled on a hybrid approach. Build a new system that uses the current pseudorandom generator behind the scenes in such a way that existing libraries could benefit from it. Which brings us to the part of the talk where I tell you what we developed and how it works. The core functionality of Clotho's parametric randomness is handled by a struct. The struct, which we call the random source struct, consists of 4 fields. First, and perhaps most importantly, is the BTS byte string, which contains an encoding of the randomness parameters we talked about in the Minesweeper example. This byte string is guaranteed to always have at least 4 bytes, which we'll come to in a moment. All of the critical functionality of Clotho derives from this field. Next is an integer index into that byte string. This is used during playback-style random generation, where we simply use the values encoded in the byte string. Third is the PRG, a Racket standard pseudorandom generator. This pseudorandom generator is seeded with the first 4 bytes of the byte string that we mentioned previously. If there are enough random generation events to exhaust the byte string, which is, after all, finite in length, further values will be generated using this pseudorandom generator. It's crucial that this generator's seed is recorded in the byte string because this ensures that reruns with a limited byte string are deterministically consistent with one another. And lastly, we have the add list. When the byte string is exhausted and new values are generated from the PRG, we cons those new values onto the add list for safekeeping. When the user eventually requests the byte string, a functionality we'll discuss in more detail shortly, the contents of the add list are reversed and converted into bytes to be stored in the byte string. I promised some more details about that byte string though, so let's go ahead and take a look. Earlier in this talk, in the section explaining about parametric randomness, I showed this slide. What, you didn't think I'd make a Racket presentation without some meta slides, did you? In this slide, we see how the perceived random values really correspond to parameters, which are encoded in something. And that something is what can be fed back into the system to manipulate randomness in subsequent program iterations. Well, you guessed it, that something is the byte string. Let's take a closer look at it, knowing what we know now about Clotho's internal struct. So here we're visualizing just the parameters and the byte string. Note that from this point on, we won't be looking at any specific random values generated by this byte string. Here's a concrete example of a byte string that could correspond to 4 randomly generated values. This is kind of gross to look at though, so let me convert it into a numerical representation. It's a bit better. Each integer in this visualization represents a byte, but this is just a long string of bytes now. How do they work? Clotho uses 4 byte chunks to represent integers internally, so let's divide this up into those chunks. Excellent. Now we have 5 chunks of 4 bytes each. Remember that the first chunk is reserved for seeding the pseudo-random generator stored in Clotho's internal struct, so to encode 4 random generation parameters requires 5 of these 4 byte chunks. As you might have guessed by now, each of the 4 byte chunks following the initial pseudo-random generator seed chunk is a parameter. I'll explain how the user can access and manipulate these a bit later. So we've gone over the implementation of the random source struct, the most critical component of the Clotho library, and I've shown you the details of how its internal byte string works. Let's talk a bit about how users can actually use the Clotho library. The random source struct itself is not provided externally. Instead, the struct's functionality is exposed through a Racket parameter named currentRandomSource. To ensure invariants of the struct's construction are maintained, and to avoid the complexities of multiple case-specific constructor functions, we provide a single smart constructor that can create new random source structs to be used in parameterization. The final struct supporting functionality is the getCurrentRandomSource byte string function, which exposes the internal byte string to the user. The byte string can then be manipulated as needed and fed back in to the makeRandomSource constructor for subsequent random generations. Of course, Clotho also provides functionality that actually uses the random source. The core randomness function is the aptly named random function. Externally, this works just like Racket's built-in random function, but internally, this is where the random source struct's byte string gets used to deterministically influence random generation. The details of this process are given in the paper. In addition to random, Clotho offers some convenience functions for easier random generation of common simple data types. All of these functions are implemented in terms of the random function. We also implemented some macros to support certain advanced functionality. If you need to use a function that depends on Racket's built-in randomness capabilities, maybe from a library written by somebody else, you can wrap calls to that function so that it will still participate in Clotho's parametric randomness by using the wrap external randomness form. If you want to import a library that provides a lot of these functions, such as the math distributions library that ships with Racket by default, you can use the require Clotho wrapped form when you require it, and all the library's exported functions will be wrapped with wrap external randomness automatically. Lastly, we provide a mechanism for what we call randomness abstraction. That's our own term, so I'll explain it in more detail. Let's go back to the original Minesweeper example where the player loses on the 4th move. But imagine we had played 2 more games immediately afterwards. So the player lost the first game due to picking a bomb. Then they lost the second game because they made an illegal move. And the third game they won. Because all of these games were played consecutively with a single random source, the parameters are all part of the same byte string. Let's say we decide to focus on that 4th parameter, the one that caused the player to lose the first game. So we modify it, leaving the rest of the byte string intact. Then we play the games again. It looks like the player won the first game, which is great. But the second game is lost again due to a different illegal move, and the third game is lost due to picking a bomb. This is disappointing because we had originally won that third game. This happened because when we adjusted the 4th parameter, it caused the first game to not lose at the 4th move. Since the rest of the parameters are deterministic, the entire sequence of moves shifted forward by 2. In other words, tuning a parameter earlier in the byte sequence can have undesirable consequences for later generations if that modification causes a structural change. So let's try a different strategy. We'll use randomness abstraction. What that means is that each game's randomness parameters are correlated to a single higher level parameter. We then just use those higher level parameters to build the byte string. In this example, we'd like to correct both the first and second games, but leave the third game untouched. So we modify the appropriate clusters of bytes. When we play the first and second games with the new parameters, entirely new squares are chosen. And look, the player won the first game. More critically, though, is the fact that the third game was left completely untouched. We managed to increase the overall win percentage without having to regenerate every game. Randomness abstraction is a tool for clumping together multiple calls to randomness functions that are all used for a single purpose, and correlating them to a single parameter. For example, you can abstract the act of playing a game, as we did in the example. This can be useful if you want to use a fuzz tester for your byte string manipulations, and that fuzz tester requires its input in the form of a simple byte string. We have only just begun experimenting with randomness abstraction, so let us know if you find a good use for it in your own project. We return now to the final component of the Clotho library, hashlangs. After all, what Racket library would be complete without a hashlang or two? Actually, Clotho provides 3. For when you don't want to use any randomness, there's Clotho Racket Base. This is identical to Racket Base, except it leaves out all the randomness functionality entirely. Then there's the Clotho hashlang. This provides all the bindings in Clotho Racket Base, as well as the functions and values needed to use parametric randomness. However, you cannot invoke any of the randomness functions outside of a context in which the current random source has been parameterized, or you'll get an error. We felt this was the right approach because we wanted to help users avoid accidentally invoking randomness functions in a non-parametric way. This might not always be what you want, though. So we also provide hashlang Clotho stateful. This is similar to hashlang Clotho, except the current random source will be initialized automatically, just like how hashlang Racket Base works. There are also a few extra forms for manipulating the top-level random source if needed, which are detailed in the documentation. This brings us to the last big question. Why did we go through all of this in the first place? What could we possibly have been up to that required us to develop Clotho? Well, we work on a project called Xsmith, which is the spiritual successor to CSmith, if you've heard of that. Xsmith is a library for building effective fuzz testers for any language you like by taking a language specification and producing random programs written in that language. But the problem space for generating random programs is absolutely gigantic, and this corresponds to an enormous tree of randomly made decisions. If one of the randomly generated programs reveals an attribute that is interesting, for example, perhaps it causes a bug despite your specification being correct, then you probably want to investigate nearby branches of the decision tree to see if there are adjacent interesting programs. While investigating what other people have done to accomplish this, we found the recently published paper, Semantic Fuzzing with Zest. While implementing the solution within Xsmith, we decided to instead generalize the library and make it available for use in other domains. Hence, Clotho was born. Our work on this is pretty recent, so we do not yet have any concrete results to share, but we are excited to see what the future holds for Xsmith and Clotho. With that, we've pretty much covered all of Clotho. Let's review what we've learned. We defined parametric randomness, a special system of random generation where each random generation event can be correlated to a specific tunable parameter. These parameters can then be fed back in to essentially rerun the sequence of random generations, but with changes that will produce changes in predictable locations in the output. We found that Racket's built-in randomness functionality is simply insufficient for doing this by hand. I should point out that this is reasonable, of course. Parametric randomness is a fairly niche use case, as far as we can tell. But since we wanted parametric randomness, we implemented it in the form of Clotho, a Racket library that solves all of your problems in life, so long as those problems are solved by easy parametric randomness. So where can you get Clotho? Well, we recommend just using the Racket package manager. A quick Racco package install Clotho should do the trick. But if you're really keen on going through the source code, or if you want to file a ticket on our issue tracker, you can access Clotho's Git repository at this URL. Well, that's it. I hope you enjoyed this talk about Clotho, a Racket library for parametric randomness, a paper brought to you by Pierce Darragh, that's me, William Hatch, and Eric Eide. Please feel free to contact us with any questions or comments. Thank you.
All right, great job, Pierce. Thank you.
Thanks.
Let's switch to some questions now. So first of all, okay. So someone asks at the end, one of the first questions is, where does this get used? Now, of course, you said this, that it gets used in Xsmith. Can you talk about how important it is for Xsmith? Is like Xsmith entirely based on this? Is it used pervasively throughout it? Can you talk a little bit about the way in which it's used?
Yeah, it's a little awkward, I guess. So Xsmith does use Clotho, but we haven't, let's see. I started working on Clotho because we identified this need where we wanted to be able to generate random programs. And like I said in the video, kind of iterate on programs we find that are interesting. But after I implemented Clotho, we ended up finding a lot of other ways that Xsmith needed to improve before we could really delve into it. So Xsmith does use Clotho, and you'll find, I think, pretty much all the Xsmith modules use hashling Clotho. But we haven't gone very deep into really making use of all the functionality that I implemented. That's on the docket, but as yet, not yet fully explored.
So when you say all the functionality, I'm imagining the replaying the beginning and then forking, when you find something interesting. I feel like that's the really special thing about Clotho, and my guess is that that's the thing that is the newest thing for how Xsmith works.
Yeah, exactly. So right now, Xsmith does use Clotho for handling random generation, but we don't. Okay, hang on. Let me think. So you can. What am I trying to say here? So the Clotho is used for deterministic random generation in Xsmith, and there is an option on the Xsmith command line to output the random seed that results. You can then manually modify that random seed and feed it back, or the byte string, excuse me, the BTS byte string that I had mentioned. You can then modify that file with the byte string and feed it back in. So it's supported. It's just not handled automatically, which is kind of what we want to get to, is having Xsmith do more of this for you and like really make use of the Clotho functionality without requiring the user to like understand all of the Clotho stuff.
Okay. So next question. It says that, okay, so you're only using 4 bytes for the random seed, but when I look at the documentation for random, it seems to suggest that there's a lot more than 4 bytes for the initial state of the random seed for the pseudo-random generator, because it uses the, what is it called, the Mersenne twister, which uses like much more than 32 bits. So what's going on there?
Right. The seed function in Racket, so in the implementation of Clotho, it essentially wraps every, what am I trying to say? Every time you invoke a randomness function within the context of Clotho, it creates a new Racket current pseudo-random generator. And inside of that is where it invokes the Racket random function and does some things, and all of that happens. The 4-byte chunk at the beginning that's used for seeding a random seed is used in a call to the Racket random seed function for generating the pseudo-random generator. The choice of using 4 bytes was more for consistency across the entire like Clotho library, because we wanted to be able to just use the same type, a 32-bit integer, instead of like, okay, the first chunk you have to, to use Clotho, you have to initialize it with a really big chunk and then smaller chunks or something like that. And so for our purposes, it was easier to just stick to 4-byte chunks. So yes, I guess it does limit the total amount of spaces that can be enumerated, but that's, I guess, something for future work to investigate.
Cool. Okay. So the next thing is, does your library allow you to use cryptographically safe random bytes for some random values?
Let's see. So if you create a new Clotho current random source using the make random source function, pretty sure it's called, and if you do not supply any arguments to it, it actually uses crypto random bytes to generate a new random source from scratch. So if you want just a totally like non-deterministic, I guess, I don't know if that's really the word I want to use, a current random source that's generated from nothing, that is supported. However, I will point out that we discovered today that the implementation of something in this, whether it's crypto random bytes or the Racket function vector to pseudorandom generator, one of them is not consistent across Shea scheme Racket and non-Shea scheme Racket. And this means that Clotho is actually not deterministic between different versions of Racket potentially, which is like not great. So currently we're trying to.
Is this the notorious Xmas issue number 53 that I heard about on CNN this morning?
That's right. Yes. Yeah. Wolf Blitzer covered it, I think, but yeah, that's pretty much the issue. And it was just uncovered by Paulos. And we're looking into it, but don't know much yet.
Okay.
Breaking news.
So next question. And what's the Racket special sauce in this? I mean, why isn't this just, a variant of the Haskell non-determinism monad?
Well, everything is a burrito all the way down, as we all know. The reason we did it in Racket is because Xmith is implemented in Racket. And Xmith is implemented in Racket because it makes extensive use of Racket's metaprogramming capabilities. Pretty much the entire thing is macros on macros that produce macros that are then macroed to macro things. And it's very confusing and complex. But we wanted the ability to do this deterministic random generation. And so we did it in Racket.
Great. Okay. There's a detailed question here that's from Robbie. So I'm going to read the question. And it's actually funny because we've talked about this before, so I think I actually know the answer. Okay. It seems difficult to predict the number of random numbers requested after making a change. For example, if I decide I don't like one branch deep in some tree, and I change the value for that choice, but I want the rest of the tree to be the same, I have to predict how many choices are needed for that branch. How do I do that?
You just gotta see the future and know the right answer. So no, actually, this is a use case for randomness abstraction that I mentioned. Unfortunately, it kind of requires you to figure out where this is going to be. But because so Robbie's point essentially is that if you've got this this string, right, of bytes, and you manipulate some, then it can change how things branch from that point on. If the change you make is for atomic, I guess, right? Like if you switch from generating a random integer to generating a random Boolean or something, potentially not a big change if that's like the end of the thing. But if further branching is predicated on this random value, then this can significantly alter the program flow, which is not really what you want. So in these cases, you can use randomness abstraction, which is essentially just higher level deterministic random generation, where you say, from this point on, or within the bounds of these parentheses, we are considering all of these to be bound to a single parameter. And so if you use that for the branch point, then you can manage those things.
All right, cool. So another question. So Max New with Robbie has this paper about using enumerations that is bijections between the natural numbers and trees, to do fuzz testing. And this is something that's integrated into RedX right now. So you can use RedX to either choose randomly in a space, or you can use it to enumerate the entire space. And so you can think of that enumeration as being unpredictable in the same way that randomness, that randomness is unpredictable, because although it is always going to enumerate the same way, I mean, I don't know which way that's going to be. So the question is, Clotho's deterministic randomness, how you can kind of think of that as being choosing a path in this enumeration that is extremely predictable, right? Because it's not predictable, it's deterministic, right? So can you relate those two ideas?
I'm pretty sure, actually, let me double check, but I'm pretty sure William looked into this particular paper that you're talking about, and it's referenced in our related work section. And in looking that up, I immediately forgot my train of thought. Could you just rephrase your question? Just
Sure. Bijections between the natural numbers are unpredictable but deterministic. Clotho, its goal is to explore an unpredictable, to do a random walk through a tree, and do that in a predictable way, a deterministic way, so you can go back and change one thing. So if you're also exploring an enumerable space, you could also just remember the path you took in that enumerable space, and that would be seemingly equivalent. And I'm wondering if that is a useful thing to think about, or if there's some, and what's your take on that?
I have to confess that I did not look into that part of the related work section. I was working on other bits of things.
Well, there's nothing wrong with when the person asks you, how does this relate to my work? You say, well, I don't know. You tell me how it relates to your work. So yeah. No problem. Well, cool. Go ahead.
Well, I guess, I'm not sure. I'm not sure that I want to. I don't want to risk answering something that's not correct, I guess.
That's never stopped me before, but all right, well, cool. Well, there's no more questions now. So recall that Pierce is going to be in the northwest corner. That's discussion area A. Now we're going to switch over to Gustavo's talk. I'm going to fool around on my computer a little bit to share the screen properly. So thank you again, Pierce.
Yeah, for sure. Happy to.
Hello, my name is Gustavo Massaccesi. I'm going to talk about the recovery path for chess scheme. If you have a program in Racket CS, like define x, unbox y, set box y, add 1x, it is transformed into a program chess scheme, something like unless box y error, define x, unbox y, the unsafe version of unbox. Unless number x error, unless box y error, set box y, add 1x. We want to remove this unnecessary random check, but another possibility is to replace this box y with true, and let another pass of check scheme to remove the expression. This is not the exact transformation, but it's somewhat similar. Well, a minimized version of this is unless box y error box y, and I will show a few minimized programs, but please imagine that they are part of more complex programs. We want to reduce a few common idioms like unless box x error box x. This is the previous example. When box x, this is very similar, but the second check is inside the if. When box x vector x, in this case we want to replace this if with false because the art is showing types. And in some case the checks are not explicit. For example, unbox x, box x. Here the argument of unbox is a box. Define x, box y, box x. Here we know that the result value of box is a box. Let x, box y, box x. This is very similar, but let. box y. Here we must be careful in case y has side effects. And other case for Boolean values, for example, unless x, here x is false. When x, here we are not sure that x is the true object, but if we have when x something, then the second x can be replaced with true. And other case that when equivalent x0, we know that x is 0. We want to reduce all this expression and similar case and do all of this in a time that is not quadratic. There is a lot of people that help us with this. In particular, I want to highlight Sean Sepieri, that made the implementation of the Patricia trees and fixed the few bugs. Andrew Kipp, that made the code more idiomatic and fixed a few bugs. Matthew Flatt, that read the initial implementation and gave a lot of feedback. And also I want to highlight the work of Michael Adams. He didn't work in this project, but he made a similar pass in his dissertation. The implementation is very different, but it was inspiring. The main function has 4 arguments, but we will pretend that it only has 3. The first one is IR, that is the expression that we want to reduce, and we will use recursions to reduce sub-expressions. The second one is context, that is where the expression is, usually valued, but it can be effect when the result of the expression is ignored, or it can be test when it is in the test position of a branch. This enables a few additional reductions. And the next argument is types, that is an immutable hash that connects the variables with the type, and the type can be box, vector, number, real, boolean, or it can be a quartet version of a value that we can copy from one part of the code, like true, false, null, or a fixed num, or some special case for records that are the equivalent of the starting Racket. And it has 5 return values. The first one is IR, that is the reduced expression. The second one is red, that is the type of the reduced expressions. It can be any of the previous options, or it can be false if we don't know. The next value is n-type, that is an immutable hash like the old types. It has all the information of the old types, and also all the information that we discover in IR. There is a technical detail here that it must share as much of the internal structure with type as possible. In particular, if they have the same information, they must be the same object. And the last 2 return values are useful when the expression is in the test position. And these 2 values are very tricky, and it was inspiring to see that Michael Adams can calculate them without using quadratic time. Let's see this in some simple expressions. After on box x, we know that x is a box, so we can add this information to n types. After box x, we are not sure that x is a box, but in the correct branch, we know that it is a box, so we add this in the t type. And after exact x, we know that x is a number, so we add this to n types. And in the true branch, we know that it is also exact, so we add this additional information to t types. It is more complicated when we have 2 expressions because the evaluation order in chess game is not specified. The idea is that if the time to analyze x is bounded by the length of x times the log of it, and something similar for y, and the additional time to combine what we know is bounded by the minimum of the length of x and the length of y, then the time to analyze x and y is bounded by the length of x and y times the log of it. We have to prove similar result for all the other constructions to get a global result. And if n is the total length of the program, we're telling you to multiply all of this with log of m. So the actual global result is that we can analyze all the program in a time that is like m times the log of to the 2 of n. The immutable hash are actually immutable Patricia trees. They are binary trees. We assign number to each variable and we put the even variables in one branch and the odd variables in another branch. Then we analyze modulo 4 and we put 0 and 2 here, 1 and 3 here, and so on. The idea is that it is very easy to locate a variable. For example, variable number 27, it must be somewhere here. If we have another 3, the same variable must be somewhere in the same position. So it is very easy to compare trees, and we modify a tree. Only the interesting part is affected. There is not rebalancing or something. In the implementation, the empty branches are skipped, so it is more tricky and more efficient, and it was done by Sean Sepieri. Also, we made a small modification that each tree remember how many steps were used to build it. So if we modify a variable, then the new tree has the same size, but the age of the tree is increased. For an expression like const xy, we have an initial tree that has all the old information that we already know. We analyze x and get another tree. Now, the evolution already not specified, so for y we must pick the initial tree and analyze y and get another tree. And now we must combine them. The idea is that we can use the age of the trees to pick one with few change and copy them to another tree and get a final tree. And all of this is bounded by the minimum of the length of x and the length of y. In some case, we have local variables like let x box y something or let x something unbox x. The idea is that we have the initial tree, and after analyzing the body of the expressions, we get another tree that includes x, and we want to remove it. If we simply remove it, the problem is that we get a tree that has a dirty path here. So we must remove it, but reuse the old parts of the old tree, so we get a final tree without unnecessary change. Let's see how this interacts in an example. If we have lambda of x, y, and z, and the initial tree with the types is empty, in the first expression display list car x add 1y. In car x we get the empty tree and add that x is a pair. For add 1y we must get the initial tree that is empty because the evolution order is not specified, and we add that y is a number. And now we must combine these two trees and get a final tree where x is a pair and y is a number. In the next expression, if real y set box set 0 error, for real y we pick the last tree and we get now 3 trees. In the second one we mark that y is a real number. In the then branch set box set 0, we pick the second tree and we add that set is a box. In the else branch error, we pick the third tree, and this is an error expression, so we get a special tree where everything is bottom, and now we must combine them. This is the different combination of the previous one. Well, in this particular case it is easy because this is bottom, so we just pick the other tree and we are done. Now, in the last expression display box set, we don't get more additional information, but in this case we already know that set is a box, so we can replace this with true and we get a reduced version of the function. Well, conclusions. We have a problem in Racket CS that is transformed into a problem in chess-scheme. We added a type recovery path that is useful in particular to reduce some runtime checks. We used some modified Patricia trees, and it runs in a time that is like n log 2h of n. Questions?
Excellent, Gustavo. Thank you.
Hi.
Gustavo, you've been active on the Racket mailing list for a long time, working on these compiler extensions for a long time, and it's nice to finally have the opportunity to have a RacketCon that you can be part of. I know that you're down in Brazil, so it's really great to see you here. So the first question that we have is whether or not your analysis can make use of procedure and figure out procedure checks to remove as well, because all of your examples were about data structures like boxes, conses, and numbers. So do you track procedures?
Yes, in my presentation, I cut a few parts to make it shorter, but if there is a test for procedure, then I save that information. And also if a variable is applied, it's automatically included in as a procedure in the list.
Does it also make use of things like procedure arity and figuring out which keywords are available? Can it track those details? Because refinements on the type of procedure.
For now, not. Only it's a procedure or not. For example, someday I want to include the return arity because it's very useful for another reductions, and perhaps arity also. One of the problems is that after the conversion, the functions with keyword are actually struct or record, and so it's more complicated to analyze them.
Mm-hmm. Do you do anything to look inside of containers like pairs and boxes? For instance, like that the thing inside of a box is a number?
No, not yet.
Okay. Do you have any idea about what the scale of performance improvements this has led to?
I think we made the same test with playing chess game, and we get like 10 or 15 improvement in speed. But it's difficult to know how much of this is translated to Racket, because the conversion sometimes it's more tricky, because, for example, the pairs are immutable in Racket, but they are mutable in chess scheme, something like that. It's the expansion sometimes too big to be understood completely.
Mm-hmm. Ben Greenman notes that Racket doesn't provide an unsafe application form. So because there's no unsafe application, this makes it so that typed Racket can't effectively optimize when it knows that something is a procedure.
It's the story is more complicated, because when you have the program in Racket, it is expanded to a program in chess-scheme, but it's Shemify. I don't remember the name. It was mostly written by Matthew, and it also tracks a lot of things. So in particular, I think it tracks a lot of about procedures, because it's very expensive to check that something is a procedure at runtime. So perhaps most of the parts about procedure are tracked in the Shemify part of the transformation, and also another part is tracked inside the zip type.
Great. So here's another question. Does this is this effective in eliminating some of the overhead of the contract system and Racket contract? Because that includes these checks. So does the information from a contract flow into the procedure to remove the checks inside of the procedure?
It's I think it's indirect because the contracts are sometimes include a check at the beginning of the function. So this part is understood and is used later. But if the random check is removed because, for example, type Racket is too smart and remove the check, then my part doesn't know.
So the next question is, so Racket chaperones pretend to be other values. So for instance, there's a chaperone box, which isn't really a box. How is that handled in your analysis? Does this break your analysis because it's a structure from Shea scheme? Like, are the predicates that you're checking the Shea scheme predicates or the Racket predicate? Because of course, box and Racket says yes to a chaperone box.
For now, it is analyzing only at the chess scheme level. So chaperones are just normal struct, and it's a problem. I think that I have a lot of noise here. It's a problem, and the idea is perhaps to make something like union predicates and try to think if this is a box, a real box, or it's a structure that is actually a chaperone of a box. Then we can use something later, but it is not implemented at all. And I think the problem is that once you start to add union predicates, everything is exponential unless you are very careful. And the idea is that this pass must be very fast.
Do you have an idea of the scale at which chaperones are getting in the way of this analysis? Like, because my impression is that chaperones are pervasive throughout Racket. And so because I assume that they're pervasive in code that use the contract system, that makes me think that this analysis would rarely apply.
I think it's a problem, but sometimes they are, for some structure like pairs, they are not chaperones, and so it's more easy with them. And perhaps the biggest problem are vectors, because lists and pairs don't have chaperones. Boxes are not too used, but vectors are. Vector, I think it's.
So right now your analysis runs at the Shea scheme level. Would it be appropriate to include analysis like this at the Racket level to remove Racket runtime checks, which we know are going to turn into Shea scheme runtime checks?
Yes, just for this to Racket. I think it's possible. One problem is that they use the NanoPass framework, so it has it has a lot of magic. Some part of the code are very short in the NanoPass framework, and it's possible to expand them, but it requires more code.
I see.
It's possible, but.
So this talk was about your last project that you've been working on for a while. Can you tell us anything about what your next project is going to be working on, or are you still polishing this?
No, my well, I think this year is a very strange year, but hopefully next year is more useful. But my idea is to try to work in something like understand how the programs are transformed and make the transformation from Racket to chess scheme more easy to understand later, and make the later optimization in chess scheme understand better the usual structure in the transformation. So try to glue them and fix some problems that appear in the translation.
Awesome. Well, cool. Well, thank you so much, Gustavo. So I'm going to clap on behalf of everybody. Give you some snaps too. Thank you very much. So we'll now switch back to the gather. So we'll have Pierce in the discussion area A, that's northwest, Gustavo in discussion area B, that's northeast. Remember that RacketCon starts again tomorrow. So at 10 a.m. Eastern time tomorrow, we'll have the State of Racket talk from Sam, and then the Racket Town Hall. And then we have a full plate of talks tomorrow as well. So thank you all for coming, you all out there on the stream, and I'll see you in a moment on the gather. Thank you so much.